Space appears smooth and endless, but a growing body of physics suggests this continuity is an illusion, that reality is actually a discrete, pixelated grid of information computing itself step by step. This is the premise of the topic ledger theory. To test whether the universe operates as a massive computer, researchers ran a 16-qubit quantum simulation on Google Cloud Platform servers to model these fundamental interactions. In this first experiment, a quantum neural network attempted to navigate a chaotic field of data points to solve a 128-bit XOR cipher. This task tested if an AI's trial-and-error learning could navigate the fundamental logic required to assemble a reality. The AI failed. It became trapped in what researchers called the catch-22 paradox, where every attempt to learn the system's rules only obscured them further. This maps the barren plateau. Measuring the entire 16-qubit system at once maximizes friction, leaving a featureless plane with no gradient. If the AI measures qubits individually to find a gradient, this isolation mathematically shatters the global connections holding the entire system together. These failures suggest that a variational algorithm, which relies on probability, cannot resolve the overarching structure of the system. It implies that the engine driving the universe may rely on a more rigid computational logic than the stochastic guessing used by AI. Shifting away from the AI's S-work, the researchers moved to a second experiment, using a classical CPU to simulate Grover's algorithm and hunt for a specific 16-bit binary target. Grover's algorithm replaces trial and error with a predictable geometric rotation. By applying the formula pi/4 times the square root of the total possibilities, researchers calculate the exact steps needed. In the cloud simulation, the algorithm navigated 65,000 dimensions and arrived at the target in exactly 201 iterations. This number represents the assembly index, the mandatory number of discrete computational events required to construct this specific state. Unlike the AI's approximation, this process shows that information in a quantum ledger is built through an exact, predictable depth of sequential operations. If the construction of information is a deterministic sequence, it should be possible to reverse the ledger and watch the assembly process in the opposite direction. Attempting this reversal creates a massive computational load. Storing the entire history of a quantum circuit would instantly exceed the server's RAM, so the system must evolve the state vector one step at a time, holding only the immediate present in memory. By taking the final, organized state and running those 201 steps in reverse, we watch the specific information dissolve back into chaos. This graph tracks the von Neumann entropy during the reversal. In this theory, time is the process of information assembling from high entropy disorder into a low entropy topic. As the simulation reverses this assembly, entropy rises sharply back toward maximum chaos. This suggests the arrow of time is the observable result of a quantum ledger converging, taking a vast high-entropy superposition and focusing it into a discrete, organized reality. But the process of organizing information generates heat. To understand how the universe avoids burning itself up during this massive computation, researchers looked at the limits of the hardware itself. Experiment 4 focused on kinetic mixing, the coupling strength between photons and dark matter that allows the universe to write data to its ledger. This chart plots that coupling strength against memory corruption. If the interaction reaches a value of pi, the resulting energy overwhelms the state, scrambling the recorded information. To maintain integrity, the system must operate within an arrow-mathematical window, specifically between 0 and pi/8. This suggests a mathematical requirement for the universe, a thermal speed limit that prevents computational heat from corrupting the entire system. When we scale these 16-qubit findings from the cloud server up to the macroscopic scale of the observable universe, the numbers begin to align. We can calculate the universe's assembly index by taking its age and dividing it by the Planck time, the smallest unit of duration allowed by physics. This results in approximately 8 × 10⁻⁶ discrete collision events occurring since the beginning of time. Using our earlier rotation constant to find the total informational capacity required to produce those events, we arrive at a phase space of 10 to the 122nd power dimensions. This number matches the Bekenstein-Hawking bound, the theoretical limit of information that can exist within our universe. The experiments on a local server mirror these cosmic laws. They suggest the universe is not just space and matter, but a structured ledger of discrete, computable events.